By the way, do you guys have a session on DRAM before?
Yes, sir.
Okay, so you guys are familiar with DRAM sort of timing parameters, at least a little bit, right? Okay, I'm just going to take the silence as a yes. So at a very high level, so there are three main timing parameters that are important to DRAM. One is the column access time. The other one is the row precharge time, and the third one is the RCD, which is row to columns delay. And I mean, there are a whole bunch of other timing parameters as well, but these are from an architectural modeling perspective, one of the most important ones, even to get a very basic model of DRAM up and running, right? So as you know, DRAM, because of signal integrity issues, you can only do certain activities after a time differential between some of the other activities have been done. And that's one of the reasons why you have various types of DRAM timing parameters that are there. Let's start with TCAS, column access. Anybody can tell me what a column access timing is and why is that important, or what it signifies really?
Do not remember that well, but the time required to put the word lines to a differential voltage VDD by 2 on both ends.
Okay, so if you want to abstract it out a little bit in terms of getting data out of the DRAM, remember we're thinking in terms of architectural sort of designs over here, right? So if you want to rise one level of abstraction higher above, what is, or what are the things that you would have to do in order to get your data out of the DRAM? Let's start there. Let's start there. Maybe then we'll sort of have a discussion on that. So assume that this is what my DIM looks like, what is being shown over here. And now I want to read some data out of this DRAM, right? What do I have to do? Anybody?
Identify the bank, identify the column, identify the row, and then retrieve the data from that.
Okay. And is this the only thing that we have to do, or there are certain things that you have kind of missed out architecturally that you also have to select? You're right. I mean, all of those things that you have said needs to be done. What before that?
Decoding the address to find where it actually lies.
Okay, so let's start with the address. That's excellent. So you're given a physical address. You wanted to look up the data for that physical address. You looked up the caches. You didn't find anything there. You have looked up all 3, 4, 5 levels of caches. Found a miss everywhere. Now that address is transferred onto the memory controller, right? The DRAM memory controller. What does the controller do now?
The controller.
So let's keep it simple and say it's a read request, right? So read request with a physical address.
If it checks in the memory, if we don't have it, we might have to retrieve it from the permanent storage, so solid state storage.
Okay, let's also keep the discussion. That's a good point, but let's keep it simple and say that it's there somewhere in memory, right? So whatever data that I'm looking for, it's at a physical address, and that information is there. What does the memory controller do now? And anybody else can jump in. Maybe I can start cold calling people if that's okay. Maybe Naman, if you want to take this. Naman Purohit.
I did not understand.
You have a physical address. It goes to the memory controller. What do you have to do now to be able to look up your information from the DRAM? Or you being the memory controller, of course. Okay, maybe I'll just go through this list since people are here. Prithvi Raj.
Yeah, so first we take the rows. So we need to let's say the column gives exactly the data which we need, and then first we do the pre-charge from the row, and once it's charged, then means that we got the row where the data lies, and then the next thing is to access the columns where we get the exact number of bits which we need from the particular row.
Okay, so that has to happen eventually, but that has to happen after a few other things have to be done as well. So the assumption that you're making, Prithvi, is that you already know what row, what column you have to access. But so far that hasn't happened. The only thing that has happened so far is the physical address with a read request has been given to the memory controller. What has to happen now? Let me ask somebody else. Shirley Miranda, maybe you want to take that?
Whether maybe to check if the bus is free or is it occupied.
Okay, that also has to happen afterwards, even just before that. So this is the first
address
thing that,
read.
Okay, address read.
From the lookup table, we have to fetch the address.
Okay, and then okay, never mind. That's completely fine. Feel free to pass it if you don't have it, but I'll keep going down the list. Maybe let me ask Tarun Sharma.
Maybe the memory controller, it can first generate the row activation signal.
Okay. So remember, a typical CPU. Let me sort of backtrack a little bit and maybe give you a more abstract picture of what this memory system looks like, right? So I have a CPU. A CPU has multiple channels, which are essentially buses, and that are sort of hanging off of the CPU. And each one of these channels is capable of having multiple DIMMs, right? So let's say I have a CPU with 4 channels, and each one of these channels can have multiple DIMMs that looks exactly like the one that is shown in the figure over here, right? So now this is what my memory system looks like, and what I have so far is a physical address that has been given to the memory controller that sits on the chip. What's the first thing the memory controller has to do? Given what I have just described, let me just ask somebody. Oh, sorry, go ahead. Yeah.
Find the DIMM module from which you want to retrieve data.
Okay. Even before that, so how do you get to the DIMM module? You're on the right track.
Which memory stick the data is going to lie in, and
Okay.
from that, inside that stick there'll be like say 8 DIMM modules. Then you have like 3 bits of address which will be dedicated to finding the DIMM module. You use those 3 bits to take the go to that DIMM address, and then from that you find out the bank and the row and column and that.
Almost there. Somebody wants to take this and just sort of run to the finish line with what Aditya said. So I have a CPU with 4 channels, and each one of these channels has, let's say, 2 DIMMs. So I have a total of 8 DIMMs. Each one of these 8 or each this aggregate of 8 DIMMs essentially constitutes the combined physical address space that I have, right, which has been divided across these 4 channels that I have. Right. I have a physical address. I have to get to a DIMM. What do I need to decode first? Okay, think about this as going from Lucknow to Kanpur, right, or someplace, to 2 cities. And let's abstract out the cities as just blobs, right? So you have a blob which is Lucknow. There's another blob that is Kanpur, and they're connected by a highway. What is the first thing that you have to do to start your journey from Lucknow to Kanpur?
Decide a mode of transportation.
Absolutely. Okay. And let's say I have decided that for you, so, which is essentially electron transport over metallic wires, right? So that has been decided. What's the next thing that you do? You get into your car. What next? You gotten out of Lucknow. What do you do now?
GPS and find the directions.
Okay. You've gotten the directions. What do the directions tell you?
Where to go. How to go there.
How to go there, right? Exactly. So what you need to do, essentially what I was trying to get at, was that you need to get out of Lucknow and hit the highway, right? So you need to hit the highway first so that you can be on your way to Kanpur, which is essentially exactly what you have to do over here, right? You have a physical address, the memory controller gives you, or a memory controller gets that physical address, and then tries to figure out which highway does it have to route this request on, which is essentially trying to figure out the channel, right? Channel is nothing but your highway that connects your Lucknow, which is your memory controller, to all these different cities, which are essentially your DIM modules, right? And the address that you want to read your information from is essentially sitting on one of these DIM modules. To get to, let's say, DIM number 2, which sits on channel number 1, you have to first figure out that I have to go on to, I have to hop onto channel 1, or the address bus of channel 1, so that I can get to DIM number so and so, on which my physical address resides, right? So I sort of decide, okay, out of these 4 available channel options, I take this one. I go to that DIM over there. So I've now figured out the DIM. What do I need to figure out next? There's one more missing step in the sequence of things that we have talked about so far that nobody has kind of mentioned. There's one more logical architectural detail that you have to figure out, and it's somewhat sitting there on this figure, but it's not been explicitly mentioned. Before you get to the bank and after you get to the DIM, what do you need to get to?
Memory controller.
Memory controller is the first thing that you hit, right? So you've gone to the memory controller. Now you're off chip. So you need you're on. Sorry.
Buffer.
Not the buffer. So you need to hit the bank. Aditya said before, you need to hit the bank eventually to figure out. But between DIM and bank, there sits one more level of logical abstraction that you have to figure out. So if you look at a DIM, and let me give you another hint. If you look at a DIM, there are 2 sides to a DIM, right? And on a typical sort of a commodity DIM, you'll see, let's say, 8 chips on one side and 8 chips on the other side. And logically, these 8 chips sort of form something like a logical architectural abstraction. Does anybody remember what that is? This entire set of 1, 2, 3, 4, 5, 6, 7, 8 chips together.
The memory stick.
Rank.
Who was that? Who said rank?
Me, rank, I guess.
Yes. Was it you, Shirley?
Sriniti.
Sriniti. Oh, okay. Sorry, I can't see anybody, so I'm just sort of randomly picking names. Sorry. Yes, but that's absolutely correct. That's the rank, right? So essentially, the first thing you do after your request goes to the memory controller is you take a look at that physical address and you kind of strip out bits of information, right? This is the channel that I want to hit. Okay, this is the sort of the DIM that I want to hit. Fine. The rank on the DIM, right? Because each DIM has multiple ranks. It could be rank 0, which is 8 chips on this side, or rank 1, which is 8 chips on the other side, right? Now I have figured out that I want to hit rank 0 on DIM 0. Then I say, well, okay, which one of these banks, of the 8 possible banks that are there on DIM 0 that I want to hit? Then, within the bank, there is a row, there's a column, so on and so forth. Right? So there's a sequence of steps, which essentially goes from looking at the physical address in the memory controller, stripping out all of these pieces of information, which tell you exactly where your information is located. You go and sort of read out that information. Excellent. So this is sort of the kind of work that we have to do to get information or to get to a particular location or the DRAM or array of the DRAM where my information is actually stored, right? So once you have figured out the bank on a particular DIM, on a particular rank, you have a bank figured out within the row, then you say, well, okay, I want to read out these sort of bits of information. And then you being the memory controller, kind of issue out these commands, these DRAM specific commands that say, well, okay, go and activate this particular row, right? And then read out these many columns or these many bits from that particular row. right? So you first activate the row. Let's assume nothing has been activated before. So you activate the row. When the row has been activated, um, it's brought down to the sense amplifiers, and then you read the appropriate bits that you want from that sense amplifiers, right? So the column access delay is essentially, I mean, and again, some sort of abstracting it out a little bit, but the column access delay is the amount of time it takes to actually read your data out of your sense amplifiers from an architectural perspective, at least, right? RCD is row to column delay. And let me just go back to the slide, sorry. Right. So RCD is row to column delay, which essentially means that there is a certain amount of time. So you have to first activate the row, and when activating the row essentially means taking that row and bringing it down to the sense amplifier. That takes a finite amount of time, right? So you have read this particular row of your array and you have brought it down to sense amplifiers. It's a non-zero amount of time. So you have to wait that non-zero amount of time and plus some more so that you can allow the signals to kind of settle down and read the information of the sense amplifiers, right? So that is why there is a row to column delay. So we've covered this one, which is TCAS, and we have covered this one, TRCD. Does anybody know why do we need a pre-charge time, or why do we have this extra element for pre-charge? From an architectural perspective, I'm asking. So you'd have to think a little bit higher above the sort of circuit level of abstraction to some extent. Why would a pre-charge be required, or when is a pre-charge required rather? Okay. Sorry, go
To
ahead.
ensure
Isn't it to make...
yeah, you can continue. Sorry.
No, go on.
Yeah, so to mainly to ensure that the charge on the capacitor is not lost, so that we don't read the wrong data or something.
Okay. Somebody else was speaking as well. Sorry, I can't see anybody.
I was gonna say to make the row active.
Okay, that's quite literal, but we talked about the row activation before, right? So anybody else wants to hazard a guess? So okay, let me kind of give you some more examples and try to help everyone arrive at a conclusion, right? So okay, I'll go back to this other figure over here, and I'll point to this thing which I've kind of labeled the row buffer. Anybody know what the row buffer is? I'll come back to the pre-charge in just a bit, but let me talk about the row buffer a little bit. Anybody remember what a row buffer is and why is it important? Okay, I'll backtrack just a little bit more. Can anybody tell me what spatio-temporal locality means and why is it important in system design?
If we use any kind of for loop or any kind of like if you take any program, it's going to be something sequential. So there's some kind of a spatial locality, and if you have a for loop, you'll have some temporal locality because you'll come back to the same statement again and again. So
Okay.
that is that's the principle behind like having cache and all, because you can essentially predict what data would be required later on.
To some extent, that is correct, right? So spatial locality is locality in space, and the space that we're talking about is that of memory addresses, right? So what that essentially means, if I touch memory address A, there's a high chance that I'm going to touch memory address A plus 1, A plus 2, A plus 3, A plus 4, so on and so forth, right? So there's a locality in space for that in that sense. And temporal locality is locality in time, which essentially means if I, at this point in time, I try to read address A, there's a very high probability that I'll try to read that address A again in let's say another time delta from now, right? And that goes back to the example about for loops, right? So if I'm iterating through a loop again and again, or iterating through an array again and again, I'll touch the first element now, go through the entire thing again, come back here, touch the first element again. So there is a time delta that happens while I'm iterating through the loop, and after that time delta, I'm going to touch that touch that element again, right? So, and that's one of the reasons why we bring in more data that's required into caches, right? Even though typically when you're doing some operation, you only require one register worth of data, which is 32 bits or 64 bits, depending on your implementation. You typically bring in one cache line worth of data. So 8 bits, or let's say 64 bits is 8 bytes of information. But we bring in 64 bytes of information in one cache. Now 128 bytes of information in one cache line, exactly because of this reason, right? Because the idea is that consecutive addresses are within one cache line. And if I have touched some address within this cache line, there's a high probability that I'll touch some other address within that cache line because of spatial locality at some later point in time. So that's why instead of, even though when we just require 8 bytes of information, we bring in 64 bytes of information into the caches, right? Now, given this kind of a long-winded background, so again, when your caches are, or when you have a miss in the cache, you have to refill your cache with a cache line worth of information, which is 64 bytes. But when I read information out of DRAM, right, I don't read 64 bytes at a time. I read 4 kilobytes at a time. Why do I do that? Does the question make sense?
We are essentially fetching pages instead of
Okay, but why am I
cache line
fetching pages?
because it's going to take a lot of time to access from DRAM.
Okay.
So if we kind of have a much larger backup, then I can keep refilling my cache using the nearby data lines in the page.
Okay, so what am I hoping for over here to happen? You're on the right track, absolutely. So I say that, okay, I wanted to.
We're hoping that the next request will request the thing that we just got.
Not quite. So you're right about the next request, and you are also sort of right about what we just got. But I am reading 4 kilobytes worth of data, which is fitting into this row buffer thing over here. And just for the sake of argument, let's assume it's 4 kilobytes, right? It's a large entity. And out of this 4 kilobytes, I only need 64 bytes because that was the amount of information that I missed, or I have to refill in the last level cache, which is 64 bytes. My cache line is 64 bytes. Let's also assume. But I have read 4 kilobytes into this row buffer because I'm hoping to do what?
Exploit
What would be
the
the
temporal
characteristic?
locality and the spatial locality so that I can use the addresses nearby. So next time I have a request, I don't need to go back to that particular row and particular column and retrieve all the data. I can just go to the row buffer and take the ones nearby.
Absolutely, absolutely right. So the idea is exactly what Aditya mentioned. So you bring in. So first of all, remember, every time you go to another level in your hierarchy, from your SRAM to your DRAM to SSD to over the network, whatever, the latency increases by multiple orders of magnitude, right? So just the devices themselves, as compared to this level of your hierarchy, become super slow. So anytime you want to access those devices, you want to amortize your overheads of reading the data from those devices, right? So that's the first point that we always do, which is essentially based on spatial and temporal locality, right? And this is exactly what we do over here, right? So I had to go and read 64. I have to bring back 64 bytes of information into the cache. But I figure out that, okay, these 64 bytes of information map to this larger 4 kilobyte chunk or a page, right? And that is that chunk that I bring down to the row buffer, hoping that if I miss in, because I have missed in this cache line, let's say cache line 20 for that to pick a number, my program, because of spatial and temporal locality, is next time going to access cache line 22 or 21 or something of that sort. And that cache line is going to be sitting in this row buffer, which I can directly sort of service off of, or I can service that cache line number 21 directly from this row buffer that's sitting here without having to do another or another high latency overhead operation of reading more information from the DRAM and bringing it back down to the row buffer, right? So basically, this is what I do. I figure out what information do I have to read, or which cache line do I have to bring back to the on-chip caches. Then I figure out which sort of this 4 kilobyte chunk or page does this cache line map to. I read out that entire 4 kilobyte chunk into this entity called the row buffer. And from this row buffer, I service out those 64 bytes of information that needs to be sent back to the CPU, right? Okay. And my hope is, again, I don't know for a fact, but all of this is kind of based on empirical evidence, right? Over when people write programs, they exhibit spatial and temporal locality. And my hope is that the next time when the program asks for cache line 21, I'd be able to just service it from the row buffer and not have to read information from the DRAM array itself, right? So that essentially makes my row buffer as something, or that makes the information that is contained in my row buffer as something very important, right? Multiple scenarios could happen. One, my row buffer is empty. There is nothing in the row buffer. So I have to first go and read information from the DRAM bank into my row buffer. That is kind of a okay-ish scenario. My best case scenario, which is going to cost me the least latency, is the information or the cache line that I'm looking for is actually within the row buffer and is there, so I don't have to read information from the array. So that's my best case information. The second sort of I don't know, second best, let's call it second best. Second best case is when there is nothing in the row buffer. The row buffer is empty, right? And I have to go to an array that I want to read, and I have to read that 4 kilobyte chunk of information into the row buffer. And from that point onwards, I send back those 64 bytes of information to the cache line. So that is my second best case, which is a little higher latency than the first or the best case that I had mentioned before, because now you actually have to bring down stuff from your arrays into the row buffer. The worst situation is when you already have some information that is sitting in the row buffer, but this does not contain the cache line that you want because it maps to some other row, right? So you can, as you can imagine, these banks have multiple rows, and your information that you require could be sitting in any one of those, let's say 512 rows. You wanted information that was in row 500, but the information that was sitting in the row buffer was for row 400, right? So now what you have to do is you have to kind of throw that data out, right? And typically you might have the case where this data that's sitting in the row buffer is actually dirty, so you have to write it back, and so on and so forth, right? So this is why, or this is one of the reasons why your row buffer management policy as to how long do you keep your information in the row buffer once you have brought it down also matters for your performance, right? Because what you really want to do is have scenarios which were the best case, which are essentially called row buffer hits, right? My information is already in the row buffer, and I want to keep hitting that so that I have the least latency access, least possible latency access for information to my successive cache lines. Whereas the worst case is when I have the worst scenario, which is essentially what is known as a row buffer conflict, where information from some other row is sitting in my row buffer, which I have to first close, right, or write back, and then bring in the row that I want and then read information out. So I have to do double work over there. And that is essentially the worst case scenario. What most controllers end up doing is sort of having some sort of a, policy where they keep the information once it has been brought down to the row buffer for some time or until some event happens, right? And that is what is known as a row buffer management policy. Once you have brought down information onto the row buffer, how long do you keep it there, or what are the events that trigger the closing of the row buffer, which essentially means the writing back of the information from the row buffer back into the arrays, so that you can maximize your best case scenarios and minimize your worst case scenarios, which are essentially your row buffer conflicts, right? Any questions on this? Does that make sense?
Yes, sir.
Okay.
Yes, sir.
So, and then finally, one thing that I'll talk about is DRAM bandwidth. So anybody wants to take a guess as to what does bandwidth mean and why could it be important? And is it always important? Let's start with what it means. Anybody wants to define DRAM bandwidth for me?
How much data can be transferred per second to the CPU from
Absolutely,
the DRAM?
Right. Okay. So that's absolutely right. And how much data can be transferred from your DRAM to the CPU per second? Okay. Is this important for every workload? Is it important for some workloads? Any guesses there?
It is required if you have a read or write intensive workload where your address is going to your cache hits are going to be a bit higher. So you just need to keep fetching from DRAM.
I'll actually, you're right about a part of it. So if it is a memory intensive workload, you might require high bandwidth, but there has to be certain characteristic of the workload that requires you to have high bandwidth and keep fetching information. And then let's say to keep things simple, we have a workload that only does reads, no writes. So only one way transfer of information, which is from the DRAM to the CPU. What does or what needs to be the characteristic of your workload in terms of its read accesses such that you might end up requiring higher DRAM bandwidth?
Random access.
Okay, why do you think that is the case?
If we have sequential access, then our caches should have that data. Whereas a random access, the chances of a cache hit is going to be very low.
Absolutely. Okay, that's great, right? So your accesses to memory should or might need to be fairly random so that you or is one of the cases in which require would you or in which one of the cases in which you would require higher DRAM bandwidth, right? Okay, the next question is, does it necessarily mean that you need one program to be doing that, or is there a situation in which a combination of programs can also cause that?
It can be a combination as well. For example, if I'm running, say, a formatter on my system, like the OS formatter on my system, and at the same time I'm trying to run a game or something. So both of them, like one of them is trying to access some data from somewhere, the other one is trying to access some data from somewhere else, and both of them are going to be memory intensive.
Absolutely, right? So essentially, it doesn't necessarily need to be. So what I'm trying to sort of illustrate over here is that your bandwidth requirements are a function of the memory access stream, access stream that your memory controller sees, right? Not necessarily what is generated by one single program, right? So if your memory controller sees that the memory accesses that are coming to it from potentially multiple programs that are running concurrently on the CPU is essentially fairly random, then this combination of programs might require higher bandwidth, right? So that's why you might see sort of server CPUs have higher number of channels typically, right? Which gives them a combined more bandwidth as compared to, let's say, the client side CPUs, which sort of go into our desktops or lower end desktops and typically our laptops, right? Because on the server side CPUs, you'll see a lot more programs just because they have so many cores. You'll see a lot more programs that are running concurrently, and the memory controller, the combined memory access stream for all of these 5 or 10 or 25 programs that you might be running on that one core, to the memory controller, that sequence of accesses seems fairly random, right? And that's one of the reasons why server-side CPUs are also equipped with more number of channels for a total higher capacity, right? Okay, so this is what I wanted to mostly discuss in terms of the various components that are associated for this particular lab, and I'll stop sharing now. What I'll request everyone to do is go through the lab document. I hope everybody has set up or done the tasks 0 and 1, which is essentially setting up the tool and running the tracer. Once you have run the results for task 2, 3, and 4, let's come back here in another, let's say, 20 minutes or so. I'll be online, so just in case you have any problems, feel free to ping me. And let's start discussing the results for tasks 2, 3, and 4. Right, and then we'll sort of try and understand why a particular type of workload is behaving a certain way. So I'll just stop sharing right now. Please go ahead and then start doing the experiments, and just ping me in case you have any problems. I'm right here. Let's tentatively plan to 3:35 to start discussing our results. All right. If anybody's done those experiments, has the numbers ready, wants to present, we can start discussing whenever you guys are ready. So whoever has run the experiments wants to sort of present the results. I don't have any numbers to discuss. I will just depend on you guys to share the results and either comment and then we can discuss the results. So I'm here whenever anybody is ready with the results. Feel free to ping and present and we can discuss.
Sir, a few minutes more.
Sure. Go ahead, please. Yeah.
So I finished task 2.
Sure. Yep.
When I quadruple TCAS, I'm getting a reduction in the time required.
Can you put those in a spreadsheet and share that if possible, or just a screenshot on the? That'd be better. I don't have the numbers handy with me.
So I sent it in the channels.
Okay, let me just quickly take a look. Okay. Do you want to comment on what is happening and why?
So I'm confused because I expected it to increase sometime, but then in all 3 cases it's lower. I mean, in this case it is lower than the other 3 cases. So
This is the IPC, right?
okay, yeah.
Okay.
Here
Um,
our column access time is increasing.
huh.
And,
So let's look at the first one, just the cache miss random. The other one will leave for later. But so the default is with the default timing parameters, right?
yes, sir.
Okay. And now let's take the first row where you increase the TRCD to quadruple the amount.
Yes, sir.
Okay. What does that mean in terms of what we had discussed? So what latency increases in this case? One more question. When you move on from the second row to 4 times TRCD to 4 times TCAS, did you keep everything else the default value and
Yes,
just
it's back to the original value.
Oh, okay, great. Okay. So in this case, there are these 3 sort of numbers that you are changing. Let's look at default. So default is 0.3 IPC, right? 0.3 instructions per cycle. Now, if you change the RCD to 4 times the original value, there is approximately what is that?
30% loss.
Sorry.
Around 30% loss.
30% loss. Yeah, approximately 30% loss. 30% loss in IPC because of what? Because of the increase in latency of which one of these operations that we had talked about when you increase the RCD?
RCD is row
to column delay.
Row to column delay.
So basically, you have increased the latency of the operation of bringing down something from the array into the row buffer, right? To 4 times the value.
Yes, sir.
Right. And what this is showing is that this particular program is very sensitive to that as well. Because it results in a 30% loss in IPC.
Because you are refilling the row buffer every time because it's some kind of random access.
Right. So it exactly is. It's a random access stream, right?
Yeah.
This program is designed for random accesses. And if you see that both for RCD reduction, for TCAS reduction, or increase in the latency, for both of these, all 3 of these parameters, this particular workload suffers significant slowdown. It's approximately in the 30-35% range for all of them. Right?
Yes.
Whereas if you look at the other one, which is strided accesses, right? There is only one reduction that or that affects the IPC by a significant fraction. The rest of them don't seem to matter as much.
Yes, sir.
right? And that is TCAS.
That will happen all the time, whereas the other two will happen only when you're transferring the data to the row buffer or that. So
Right,
that's
right. So the characteristic of strided access is essentially it's a sequential access to some extent, if you want to think about it that way, right? So the idea is that so you have to bring stuff down into the row buffer, and then you have to read out that information. So you have brought it down to the row buffer, and then you issue a column read thing, which initially was X latency, right? Or TCAS latency. So your overall or your overall time for executing a memory operation was dependent on that TCAS being the primary component, because it's a sequential access. So once you have brought it down, you have amortized the costs of bringing down the information into the row buffer. The only thing or the only latency that you pay again and again is TCAS, right? So you access this first set of columns and the second set of columns, and the third set of columns. And for each set of columns that you access, you have to pay TCAS latency, which becomes the predominant latency in your memory access latency, right? So as soon as you change that value to 4 times the original value, then you see all of a sudden your IPC drops significantly, because now each one of your memory accesses, let's say in the steady state initially was causing or was TCAS. Now it is 4 times TCAS, right? So I mean, of course, the drop in IPC is not linear. So your average memory access latency is going up by approximately 4 times in the steady state, and that results in a 50% drop in IPC. Whereas that is not the case in any of the other two cases, right? Because and do you want to sort of comment on why that is the case? So why is TRCD, quadrupling the TRCD, not really causing any or causing a significant drop in IPC? It's going from, let's say, 104 to 100, like 400 or a 4% drop in IPC.
I guess it's because of the reason we discussed before. Like we discussed that the like we have a 4 kilobyte row buffer which you are fetching, whereas we have only 64 bytes or whatever of cache. So you access your memory very less frequently. Like you have to go back and take the row very less frequently compared to taking every number of times you're going to hit the DRAM. So.
Right. So absolutely, what has happened here is that you have kind of amortized. So as I mentioned before, right, in this particular case, TCAS, the value of TCAS is basically the predominant component of your memory access latency, because this is sequential access. Once you have brought it down, you pay the latency of bringing down stuff into the row buffer, which is TRCD, once, and then you pay, let's say, 500 TCAS worth of latency to read all the information out from the row buffer one by one, because it's sequential access, right? So your TRCD, increasing the TRCD to 4 times, is not causing a significant drop because it's happening very infrequently, right? So you pay 1 TRCD worth of latency and then hundreds of TCAS worth of latency. So it's again sort of Amdahl's law in action to some extent, right? Your common case, which is your TCAS in this particular case for cache occupied stride stream, is something that you are doing again and again, which is the common case. And as soon as you increase the latency of your common case, your overall performance suffers, right? Similar is the case with TRP in this case, right? So there are not that many row buffer conflicts that are happening either, right? So increasing the TRP by 4 times as much doesn't affect the overall performance of your workload because it's not happening very frequently, right? That makes sense?
Yes, sir.
Cool.
And
Excellent.
sir, is it also because of the spatial locality? I mean, because it's a strided access, and does it have any effect because of less reduction in the IPC here?
So it's because of the sequential access is the reason why you are seeing this behavior, right? You're not seeing this behavior in the random access stream, in which increasing each one of them essentially decreases your IPC by approximately, let's say, 30%, right? Whereas in this case, the sequential case, which is the right one, only one, which is your TCAS, which is the most common case, essentially reduces your IPC by a significant amount. Everything else doesn't reduce it by as much because of what the workload is doing, which is accessing memory address sequentially, right? So there's a lot of spatial locality because of which this is the behavior that we are experiencing. Does that make sense?
Okay, thank you.
Cool. Anything on the row buffer or channel width? Anybody else wants to take that?
For row buffer also, in row buffer, I'm getting very little reduction when it is a random access, whereas for the strided access, as it's reducing by 0.03 APC. So 30.
Can you also paste that? Sorry,
Yes, sir. I'm getting the results for the
okay. Yeah.
Mm.
Whenever you get just this like this, it's good. Can I look at the numbers and discuss?
I've updated. I've replied to my original message.
Okay. Okay. So let's look at cache occupied stride stream, the right one, which seems to be the more important or more interesting one, right? So what we need to compare are the row which is titled default and the row which is titled row buffer miss, right? And there's, as you can see, there's a significant drop in IPC, approximately 30% here as well, right? Why do you think that is the case?
In random access, the row buffer does not help in any way, whereas when you are performing strided access, our data is going to be present in the row buffer, hopefully. So here we can see that when we are missing, there's an increase in the time required to fetch any data, because you need to copy the buffer and do it.
Right. And this is exactly the rationale that we had sort of arrived at for TCAS, right? In TCAS, so for the sequential access, which is cache occupied stride stream, the common case for the memory latency is the TCAS value, right? So as soon as you increase the TCAS value, you end up paying a higher latency for every memory access because the common case of accessing sequential columns increases. Now let's look at the row buffer case. So initially what was happening was I brought something down to the row buffer in the sequential workload, and I kept accessing the columns until I was done reading the entire row buffer, right? Which essentially meant that I was paying a bunch of TCAS latencies for reading that entire 4 kilobyte row buffer, which was based on the assumption that I had kept the row buffer open, which is, all the information once it has been brought down, sitting there until unless I explicitly close it to bring something else in. Whereas what I'm doing in a row buffer miss in this particular row is I try to, this is a sequential access workload, right? So it's trying to access sequential accesses. And it would be beneficial for me to keep that row open, to keep the row buffer, the contents of the row buffer as is until I'm done reading the entire row. What the row buffer miss thing is doing over here is that it tries to access the first cache line in the row buffer. To do that, it brings the entire row buffer down. It reads that cache line and it closes this as soon as this particular cache line is done. Right? So the next time you have to read the second cache line in the row, you have to bring that particular row down again into the row buffer and read that cache line. As soon as that is done, it's closed again. So the next third one, which again is happening because of how the workload is essentially written, or how the workload tries to access its memory. If you read in a cache line, or you try to read a cache line out of the row buffer, and then you close it automatically such that it's a row buffer miss. And because of this, now the latency to read this row into the row buffer, which is your TRCD, is also starting to play a significant role. So your memory access is not just governed by tcache, which is a very small value if you look at it, right? But it's every time you try to read something, you also have to TRCD, which is a larger value. And that's why, because of just irresponsible management of the row buffer, because you didn't take into account how the workload is behaving, you are experiencing a 30% drop in IPC. Whereas that if you look at the random access memory comparisons, right? So the row buffer miss row as well as the default row, there is not much of a difference in IPC, which essentially means that okay, anybody wants to take a guess as to what that means over here? So I'm looking at row buffer miss for cache miss random, which is 0.29, and the default for cache miss random, which is 0.30. So basically, let's say nothing's changed, right? Why has nothing changed?
Because you're not, for random access, you're not going to get much hits in the row buffer anyway. So
absolutely,
in general case, you don't have any.
Exactly. So it was all of my accesses were kind of row buffer conflicts to begin with, right? So so I haven't really lost anything in terms of IPC, so to say, right? So you can see, right? I mean, it's the exact same CPU, it's the exact same set of settings, but one particular workload suffers a 30% drop in IPC just because of one particular policy change that you did, right? I mean, you, rather than keeping your row buffers open all the time, you have closed those row buffers, causing all your memory accesses to be row buffer misses, which essentially drops the IPC for the workload which had a lot of sequential accesses, right? And then that is something that all general purpose CPUs have to kind of contend with, right? I mean, the requirements of one workload are very different from the requirements of the other workload. And then they have to constantly kind of make sure that none of these is suffering at the expense of some other thing, right? Okay, excellent. Let's see. Oh, okay. So we are at 4 p.m. anyways. I think Joycey might be joining sometime soon. Joycey, are you here?
So I think the doubt clearing session is at 4:30.
Is it at 4:30? Okay.
Yeah, I think so.
Let me just quickly check. Not entirely certain. It's okay. And in my sheet, it says 4. But anyways, let's we can keep the discussion going on until Joycey joins. So last is the channel or DRAM channel width. Right. So anybody wants to just sort of tell me a little bit about what does reducing the DRAM channel width from, what was the default value? Sorry, I completely forgot. The
default
DRAM
was
8.
We are using it to 1.
Okay. So the default value was 8, and now you change it to 1. So what does channel width of 8 really mean? I mean, what does that signify to you in terms of, you know, that number? Anybody?
Does it play a limitation on the bandwidth available?
It does, because it was kind of that was sort of a giveaway in terms of the setup of the problem. But 8 is, let's say, 8 bytes. Now 8 bytes in relation to bandwidth doesn't really mean much, but let me put it this way. the amount of data that you can transfer in one go, right, is essentially the DRAM channel width, right? I mean, you can think about the width of the bus in this case, right? So in this particular case, if your DRAM channel bus width is 8, it essentially means it can transfer 8 bytes or 64 bits in one go. If it's 1, it can transfer only 1 byte, right? So in a given window of time, if your bandwidth is, or if your channel is skinnier, right? If it's a 1 byte channel versus an 8 byte channel, in a given window of time, you can only transfer a small amount of data by changing this parameter. And I'll leave it up to you guys to sort of run the experiments and um, discuss what the implications of that might be, specifically for these two workloads that we are talking about, right? I see that Joycey is here as well, so I'll just quickly pause here, and then let's we can take questions regarding the sessions today. Hi, Joycey.
Hi, Manu.
So please feel free. This is supposed to be the doubt clearing session part of today's session. We have till 4:30. We can go on till later also if you guys have questions. So feel free to ask any other questions to either me or Joycey or
So we usually say that AMD has much more performance gains. It's much more dependent on the memory bandwidth compared to Intel. Is there any reason microarchitecturally? Because yeah, both of them are going to use the same kind of memory. So why is it different?
So that's sort of a loaded question, right? I mean, it also depends on the line of processors, how many channels are there, what generation of DDR these particular set of products are using, so on and so forth, right? So it as just sort of under a bracket of AMD products or Intel products, you can't really do a comparison as long as you have a sort of an in order to have an apples to apples comparison, you need to know how many sort of channels there are, what is the width of each channel, how many DIMMs can it support on a per channel basis. But that aside, the um, the knobs that both of these sort of companies that have to play with. So both of them have to, let's assume that they are sticking with DRAM. Both of them have to adhere to the JEDEC standard of how they talk to the DRAM DIMMs. But all of these companies have a lot of leeway in terms of the policy design and how well the policies that are implemented in the memory controllers are able to adapt to changing workload scenarios, right? So we just saw certain examples of where just a row buffer management policy can make a huge difference in performance for a given type of workload, right? So for example, let's say if you were to compare two processors, everything else remaining the same, the memory system performance would depend a lot on how well these memory controllers and the associated policies are being optimized. And then, of course, the sizing of various buffers, so on and so forth. So there is a lot of architectural as well as circuit level fine tuning that happens. But at a higher level, I think it's very hard to say whether AMD is better or Intel is better. But typically or recently, AMD products have been making more news because they have come up with a few other design points like chiplets by which they're able to scale better. But in terms of in terms of guiding memory performance, both of these companies have the same sort of knobs that they can play with. It's just that whoever designs their policies better, which is more adaptive to changing workload demands, comes out to be a winner eventually. No, it's not a great answer, but that's all I have right now.
Thanks.
Joyce ma'am.
Yes.
Yeah, I had a question related to asynchronous processes. So basically, how much is of difficulty when we think about debugging the asynchronous processor? For example, let's say when we have a combination logic, it always has the glitches and then it kind of propagates. So when we have this synchronous processor, so it's kind of confined between two registers, and then when we do the static timing analysis, we kind of get to know, okay, this is where the actual the timing violation is. But when we have this asynchronous processor, that means that the glitch can just propagate, right? So how difficult is it so like after the design to debug these kind of issues in the asynchronous processes?
Okay, so I think it is difficult in both synchronous and asynchronous. That's the answer to that question in general. So once you have designed a synchronous processor or an asynchronous processor, the timing verification, which is, which will happen due to, especially due to these hazards or, a static timing violation for any reason. Okay, so those have to be handled. So in synchronous domain, what we normally do is, if there is a timing violation, so I think there was a very interesting work which is probably called Razor, I think around 12 years back. And there the authors have explicitly handled the Razor this problem, where what they have basically done is they have designed a detection circuit. Okay, so they sort of detect that some edge which is supposed to come at a particular time is now delayed. Okay, so it's called a delayed edge detection circuit. Okay, just simply put that way. And then what is done is, so that's like detecting an error. Okay, so timing violation is detected. Now, actually, there are two parts to this problem. Okay, one is detection of an error, and the other is correction of this error. And I think correction of the error in a synchronous world is much more difficult. The reason being that if you have any timing violation, then if it's a very long pipeline, right? So what would you do? You can't do anything with the clock, right? So sometimes there are policies which some companies have shown where they would do what is called as time borrowing, which is basically saying that, okay, if I have detected a late edge at in a particular let's say in a particular stage, then the next stage will be given slightly less time if that is possible. And that way it sort of gets sorted out between two stages. But if this continues, okay, for, let's say, it happens number of times, so let's say the next stage also violates, and then it can have these kind of effects, and then one has to probably do, I think, architectural replay or something of that kind. So that is what is done in synchronous. Now in asynchronous, what happens is that actually there's a benefit, because if you see, whenever there's a timing violation, so if the controller is also made to capture this or detect this timing violation, which is not very difficult problem. So there was a work that came parallel to Razor, which was just named Blade. Okay, so just so that it is a similar kind of a work, but for asynchronous world. And what the authors have done there is that they have detected this late transition. And then in an asynchronous paradigm, what happens is that you can stall the pipeline, because each of the stages are sort of independent with respect to each other, right, in terms of timing. So you just make a stage wait. And when a stage waits, everyone else waits. Okay, that was actually the main reason why we thought that for even error analysis, it was a good idea, because whenever an error happens, you can just stall the pipeline till the error is removed. It's a soft error, right? So you just wait sufficiently long so that the error is removed, and because it's a soft error, and then you just continue as if nothing has happened. So that way, it's easier to handle, timing in case of asynchronous. But nevertheless, identifying or detecting timing violations is a non-trivial effort. Does that help?
Yeah, thank you, ma'am. Yes.
How would we interface a synchronous processor with an asynchronous processor, or a synchronous memory with an asynchronous processor?
So typically, the standard interfaces that are used, which even now I think the tools also support. Like for example, there are standard mechanisms which Cadence, for instance, support, or any such company would be able to support, which is the same as for CDC, clock domain crossing. Okay, so you don't really call it as asynchronous, you just call it as clock domain crossing, CDC. So what happens is that you use synchronizers, which is nothing but a series of flip-flops, and you're just giving more time. So it's like a multi-cycle latency before the signal is actually latched or seen by the other domain. Okay, so if you have, let's say, a keypad connected to a processor, that's the simplest example one can think of, right? Because that is always asynchronous, right? You would just synchronize it by using many synchronizers. But in general, in a setting, you would have actually multiple such synchronizers back and forth. So every time a signal comes into the synchronous world, it has to be synchronized. And whenever the synchronous domain sends out something, there's no synchronization needed, because the asynchronous world can treat it as an event. So only when a signal comes into a synchronous domain, one has to put synchronizers. And synchronizers are just chain of flip-flops.
Okay, ma'am. So won't this, if there's a multi-clock delay, then won't this negatively impact performance, especially if you're interfacing with memory, for example, which is synchronous? Then any performance gains you'll see through the asynchronous processor might be offset by the read and write latency increase because of the delays of like the registers or whatever.
Yeah, absolutely. So a multi-cycle latency is definitely, going to hit the performance. Now, actually, I'll put this answer in two ways. Okay, so first is that there are certain domains where you just cannot do away, without synchronizer. See, for example, recently people are exploring this. It's actually called UPF. So basically, whenever you have an SoC, you always want to work with the power within a certain power budget. Now, how do you budget this power? When the SoC is doing some function, you want to ensure that all the rest of the functions are, or all the rest of the IP cores are either, gated or something like that happens, right? So when you're handling these kind of situations, you automatically, your that multi-clock domain comes into picture, because, or the clock domain crossing comes into picture, because in order to reduce power, either you would reduce the clock frequency, change the clock frequency, or you would reduce voltage. Either of them will violate the timing, right? So one reason is that it's just a need. And the assumption here is that this kind of a thing happens once in a while. And generally it happens with the peripherals, which are anyway slow. And so it is okay, right? So that way there is a good bargain of power versus performance. And you're willing to pay the performance penalty to gain power. Okay, so that's the hopefully win-win situation, because peripherals are anyway slow, and then it's okay. Now you're talking about asynchronous memories. Now that's not the mainstream application of asynchronous designs. So it is not required that one should use asynchronous memories, for example, right? Something that is expected to work at certain clock ticks, or at a certain clock frequency. Why would one make it asynchronous, right? So
Synchronous memory with asynchronous processor. The processor continues to be asynchronous, whereas the memory which it's connected to is synchronous, like it's
yeah,
connected to the clock.
yeah. So we don't want to touch the memory, because it just, the whole game changes then. So
Yes, ma'am. Yes, I was talking about the processor only.
yes. So did I answer your question completely?
Yes, ma'am. Yes, ma'am.
Okay.
Thank you, ma'am.
And Yeah, and continuing with this question, so how do we halt these type of processes then? Let's say if I am waiting for a data or something, so there will be usually registers wherein we can halt in terms of synchronous processes. But how we will get to know that okay the data has been arrived so that the processes should continue, because there is no kind of retention for this. So all the values would just be going because there are so much of combinational logic. So how do we retrieve these things when we are waiting for the data?
So if I get your question right, you're basically asking how do I halt the processor?
Yes, ma'am. So it's like when in synchronous, let's say I'm waiting for a memory so that we can put the core in halt state, and then once the data is arrived, we get the acknowledgement signal so that the processor can continue. But for these type of processes, how can we do that?
So it's in fact much more simpler, because in an asynchronous world, everything happens at a request. So unlike the synchronous world, where in a synchronous world, what the processor does is that it always goes and checks. It's more like a polling mechanism, right? You keep on waiting whether something has come, whether something has come. Every cycle you would be checking. Unlike synchronous processor, in an asynchronous processor, you just wait whatever is that entity, let's say in this case, memory. So when the data comes, until the data comes, the processor need not be doing anything. So it is just going to be in the wait state. So the controller, so again, we have the control path and the data path, right? So the data path is silent, not doing any job. The control path is made silent, unlike the clock signal, which continues to tick. And as soon as the memory is ready with the data, it can just generate a request from the memory to this asynchronous processor, saying that okay, now the data is ready, and then the processor continues to do it. Now, if the memory is fast enough, and if the data comes as in every clock cycle, let's say, then it is like just generating requests fast enough. So, but it has to be like a token that, the memory tells, okay, now the data is ready, now the data is ready, now the data is ready, that kind of a thing. And then it just keeps on, taking this request and processing the instructions.
Okay,
In
got
our work, in fact, we have run a program and shown that, the instructions actually run one after the other. In fact, if you have multiple programs and if you're running only one program, then in a synchronous domain, you would run a program and then the clock would tick, but the processor wouldn't be doing anything. So it's just idle, but the clock keeps on ticking, right? Whereas in an asynchronous processor, after the program is halted, everything is, no switching happens in the complete processor, right? Because even the control path is just, it goes to as if sleep, right? Yeah.
Okay. Yeah.
You had any other question also?
Yeah, please feel free to ask questions.
If you have any questions, please ask. So if there are no questions, can we stop the session, sir? Manu sir and Joycey ma'am.
Sure, yes. Sure. Absolutely.
Thank you, Manu sir. Thank you, Joycey ma'am. Actually, loved today's session. Actually, it was very nice. Anybody have any questions?
All right then.
Okay.
Chalo.
Yeah. If there are no questions, I'll stop the recording.
Sounds good.
Yeah.